Welcome to the Explainer. Look, if you're gearing up for technical coding interviews or, just trying to level up your data structure knowledge, you absolutely know the stakes are high and time is super limited. So today, we're setting the stage to completely demystify a literal secret weapon for your coding toolkit. We are talking about priority queues.
I want you to focus on this number right here, 15. Now, why is that important? Well, because mastering this one single data structure instantly unlocks the solutions to at least 15 different LeetCode problem types. Literally. Instead of, memorizing a dozen completely disconnected algorithms, understanding the underlying mechanics of this one tool gives you a massive advantage when that clock is ticking during an interview.
Okay, let's dive into this. Section 1. What is a priority queue?
Let's look at the formal computer science definition really quick. A priority queue is a data structure designed to always give you the minimum, or sometimes the maximum element, reliably in O of log n time. That time complexity? That's the magic of it. You aren't scanning through an entire array one by one to find the smallest number, because that would take linear time, right? Instead, the structure is constantly maintaining itself. Oh, and keep this fact in your back pocket. If you're using Java, it's called exactly that, priority queue, and it operates as a min heap right out of the box by default.
But let's step back. To explain that abstract theory again through a much more practical lens, think about a real-world scheduling problem. Or, say, you're building the routing engine for a GPS app. Out of millions of possibilities, how do you actually know what to process first to always find the nearest unvisited node? Well, if you just use a standard list, your software would completely freeze up trying to check every single path. But a priority queue? It naturally bubbles that absolute nearest, shortest, or most urgent node right to the top for you to grab instantly.
Section 2. Coding in Java. So, the crucial point is how we actually take that elegant concept and turn it into real code.
The Java API makes this incredibly straightforward. Basically, there are 3 core actions you need to memorize. When you want to add an element into the queue and just let it sort itself out, you use pq.offer. Easy. Then, when you're ready to process the most urgent item, meaning you want to actually remove the minimum value and return it to use in your logic, you call pq.poll. And if you just want to look at the minimum value without actually removing it from the queue, you simply use pq.peek. Offer, poll, and peek. That's the whole engine right there.
And this brilliantly illustrates the flexibility of the structure. On the left, we've got what we just talked about, the standard min heap, which is the default state of the Java priority queue. It gives you the smallest items first. But what if your specific problem requires finding the largest, most massive element first? Well, on the right, we see the Max Heap. You don't have to write a custom class or anything crazy. You simply initialize your priority queue and pass in Collections.reverseOrder. Instantly, the behavior is totally altered, and the maximum element will now bubble up to the top. It's a real game changer.
Section 3. Advanced interview patterns. Let's see how this actually gets applied in an interview.
Okay, here's a classic pattern. Finding the top k elements. Let's say you need the 5 largest numbers in a massive stream of data. Step 1, you maintain a min heap of size k. Step 2, as you iterate through the data, for each new element, you just check if it's larger than the top of your heap. Remember, because it's a min heap, the top is the smallest of the big numbers you've saved so far. So, if the new element is bigger, you remove that top element. Step 3, you add the new element in. By the time you reach the very end of your data stream, your little heap is perfectly holding only the k largest items. Super efficient.
Another absolute heavy hitter is the k-way merge, where you have to merge k-sorted lists. Think about how elegantly the priority queue handles this. First, you add just the very first element of each of the lists right into your min heap. Next, you continuously pull the minimum value out of the heap and add it to your final result array. Finally, whichever list that minimum value just came from, you grab the next element from that specific list and drop it into the heap. You just keep this continuous flow going, pulling the minimum, adding the next inline element until all the lists are perfectly merged.
Section 4. Routing with Dijkstras. Let's move to and see how this builds into our final and maybe most powerful application.
Dijkstra's algorithm. Now this connects directly back to that real-world GPS question we were just talking about earlier. Dijkstra's is fundamentally built on the back of a priority queue. By continuously feeding unvisited paths into the queue, Dijkstra's algorithm is guaranteed to always process the nearest unvisited node first. It completely avoids wasting time wandering down long, inefficient paths because the priority queue is constantly feeding it the mathematically shortest next step.
So we end with this core takeaway. Priority queues literally are everywhere. You're going to see them dominate in graph traversals, greedy algorithms, and complex scheduling problems. Your clear call to action here: get incredibly comfortable with that Java API we walked through. Play with offer, poll, and peek until it's second nature. Because if a simple priority queue can effortlessly organize the chaos of GPS routing and continuous data streams in mere milliseconds, ask yourself, what other massive bottlenecks in your own code could this secret weapon instantly solve? Keep learning, keep building, and we'll see you in the next explainer.